Hello everyone, in this lesson we're going to be talking about linear versus nonlinear equations. We're going to look at this in a table, in a graph, and then in equations themselves. So let's start with our tables. So if we're looking at this table, we want to first start by looking at how much y is changing and how much x is changing. So I like to make little notes over here. So that went down 3 again. Oh, but this time it went down 15. This time it went down 6. This time it went down 6 again. So some of you might be like, oh, those are different numbers. That's not what I know about linear. But we can't tell that yet. We have to go ahead and look at how x is changing. So here we went up 1. Here we went up 5 again, and then up 2. All right, so when we're comparing this, we need to compare across. So the -3 over 1, that would be a slope of -3. And then we can compare the next one. All right, still a slope of -3. If we come to here, we have -15 over 5. Well, that's -3. But let's keep going. Here, we have a change of 5 in x, but we have a change of only 6 in y. So this time we have -6 over 5. That's not -3. And at this point you can stop. As soon as you find a y change compared to an x change, y divided by x to be different, you know that this is non-linear. Let's look at a second example. All right, so from here we went up 4. Here we went up 4, here we went up 4, here we went up 4, here we went up 4. A lot nicer, a lot cleaner. Let's check our x's because right now we might be thinking, oh, it's linear, it's going up by the same amount every time. All right, so we went up by 1, up by 1, up by 1, up by 2, up by 4. So if we start comparing here, that's a slope of 4, that's a slope of 4, that's a slope of 4, but here, even though we still had a change of 4 for our y values, since it's compared to a change of 2 in x, we actually have a slope of 2 there. So this one is also nonlinear. So we can't just look at y data alone, we need to look at y and x data. So let's try to sum this up. In a table of linear functions, the rate of change in y divided by the change in x must be constant for the entire or total table. Okay, so the whole way through it has to be consistent. As soon as you find one inconsistency, the table is non-linear. So when we're looking at a graph, this might be the easiest way to identify linear, because for a graph to be linear, it has to be a straight line the entire time, one continuous straight line. So let's look at a couple of non-examples. So certainly, if it's got a curve like this first one here, non-linear. It's not a straight line the whole time. But some things that often throw students off would be things like a graph that went straight for a little bit here and then straight in a different direction like that. This graph is still non-linear. It needs to be a single straight line throughout. Another thing that throws students off is a graph that would maybe go, and I guess it's really very similar, but it goes up and down like our absolute value graph. That is nonlinear. It's very rare, but there are graphs, they're called step functions, and they kind of look like this. There's like gaps in them. That would be nonlinear. We could, draw countless others. We could draw graphs like this, which we'll see more later in the course. That's nonlinear. It has to be one continuous straight line throughout the entire picture. So here's what we're going to sum this up as. In a graph of a linear function, there must be one straight line with no curves. Wonderful. Okay, so we got table, we got graph, now for equation. So this example over here is an example of a linear equation. These examples over here are all nonlinear. So there's a couple things that we're looking for in determining if an equation is nonlinear. The first one we have here is when we've got a fraction on the bottom. Filling in our blank here, this is division by a variable. I should have put them in order here, but division by a variable is a problem for us. The next case that's a problem for us is an exponent. There can be no exponents. And I should qualify this. If we look over this example here, is there an exponent on x? Yeah, there's technically an exponent of 1. So what we really mean when we don't see an exponent is that the exponent is 1. It's 1 in a linear equation. If there's an exponent of anything else, like a 2, a 3, a 4, a half, a quarter, any of those things would be non-linear. Another thing would be a product of variables. That would also be a problem. I want to add a couple other examples that are also going to be nonlinear. Some of them we might not see very often, but if we had something like y equals the square root of x, that would be nonlinear. And you could think of this as really just a case of exponents because that square root is a 1/2 exponent. There's things that we'll see in later courses like y equals sine of x. That's a trigonometric function. We haven't gotten there yet. So there are countless other things that would make this graph nonlinear that we don't necessarily include. We should include something that we have seen is y equals absolute value of x. That would also be a nonlinear case. If we think about the graph, that'd be another way that we could kind of think about, okay, a graph. What does the graph of that look like? We know it looks kind of like a V, and so that's going to be a nonlinear example. So those are the ways that tables, graphs, and equations are categorized by either linear or nonlinear.